before the break then, we showed that we needed to plot log I against log P. To prove this, we're going to put log I on the x-axis and log P on the y-axis, because if we look at the function, log P is on the y-axis and log I is on the x-axis. So we need to generate a table, and I've started it off for you. Current 1.4, 4.7, 6.8 and so on. Log of the current 0.146, 0.6 and so on. You've got to just complete the table, please, by finding the logarithm of these values. So log of 9.1 goes in here and so on. When you've done that, you've then got to make suitable scales up and plot these out on the graph paper. I've given you some graph paper. You can plot it. You can have it landscape or portrait, whichever way you think is most convenient, starting from 0 and working upwards to make sure you include the maximum value. Plot these values and you should get a straight line, and then you can draw on that line the line of best fit. Just start videoing this again. So here's our results. We put in the values. To put in these values, we found the logarithms and we plot log of I against log of P. Not an easy set of data to actually put on a piece of graph paper. So we plotted these results, plotting log I against log P, and they're not an easy set of results to plot. 0.146, 0.672, you know, as Michael has said, can I round these? You have to. It's difficult to find exactly where they are on the graph paper. And if you're plotting it by hand and you're going to get a value for the y-intercept, the y-axis and the x-axis must start at 0, otherwise you're not going to get a true value for the intercept. So perhaps I didn't make that absolutely clear before you plotted it, but both sets of axes must start at 0. Don't be tempted to start at 1 and go up to make it as convenient as possible. So once you've done that, then we can find the y-intercept from the graph that's drawn by hand and the gradient by hand. And you can imagine for a set of results, if you're in an engineering situation and you've done a little experiment, you've got some data, you've plotted the current, found the current and the power for this thing, you could have done that. You want to find this relationship between the power and the current. So you plot it. You do a little calculation because you remember your maths from college, so you can find this log relationship and you plot the straight line. If you plotted this, which you have, you've proved that it is a power relationship because you've got a straight line. And that's the first important thing. If you don't get a straight line, think again. Okay? But you have got a straight line, so you know that the relationship is of this form, P equals Ri to the n. And now you've done that, all you've got to do is find the values for the gradient and the y-intercept, and you can work out what R and n, what those values are in this formula. Okay? Now, what I want to show you is another way to do this. Software, autograph software that we're going to be using. I'm going to book the HE study area downstairs. I couldn't book it for tonight because there's someone else in there, but I'm hoping to arrange for us to go in there next week, hopefully. Certainly at some point. Let's look at how this works. So if we fire up this autograph software that is on those computers in the HE study area, we fire up autograph and you get a blank page and you can put some data points on. I've put a lot of them on to save time, but if I double click on these, I get the data set, and to enter it, you hit this button here, enter an XY data set, enter a data table in other words. So if I double click on it, you'll see that's what you get up, and I put the data points in, and if I want to enter a data point, I just hit return and it goes to the next point. So I've just got the last two to put in, which was 1.12 and 3.63. So if I go back to autograph, I hit 1.12, was it, and hit return, and then 2.63, 3.63, thank you, and hit OK, and I get these data points in, and you can see them on here. You can see it's a straight line. However, we can do a bit more than that. We can play around with these values and the way this graph's arranged to make it look better. So the first thing I'm going to do is I'm only interested in this quadrant, so this hand tool allows me to drag the graph down, so I'm looking at that right-hand quadrant. Now I want to zoom in on this part of the graph. So this box here, zoom box in, you put a box around the data point you're interested by clicking and dragging around it, and then when I release it, it zooms in on those values. Use the hand tool again to make sure I've got the origin in there, and there it is. Okay. I can actually zoom in on the x or the y axis using these to either, if I zoom in on the x axis, it zooms in on that particular part of the graph, which allows me to zoom in even more. So I've got my data points. Now what I want to do is to find the line that fits in. So I go to this point here and enter an equation. And I type in y equals mx plus c. And it puts in a line with, by default, the gradient one and the y-intercept one. So we can see the y-intercept one, and if we could work out the gradient of this line, it would be 1. I can change the values of m and c, look, by going to this button here, which is the constant controller here. And then I can change the values of the constants m and c. So all I've got to do now, I would change the value of n by making it bigger and smaller, and so I play around with that until I get the line roughly parallel with the points, which is around about now. And then I change the value of c, which shifts the line up and down until it goes through the data points. I might adjust m a bit, so I'll make m a little bit steeper, and that's not bad. Okay, m is 2. The gradient of this line is 2. So if you've done yours by hand and got a gradient of 2, that's what you should be getting, a gradient of 2. More than that, I've got that c, the y-intercept, is around about 1.4. So I can conclude from this that m equals 2 and c equals 1.4. I think you can see that autograph is a rather nice way to do it, but we've not always got graph plotting software like this available to us, so it's perfectly valid to do it by hand as well, which is what you've just been doing. Okay? Yeah, it should be exactly 2, but if you've done it by hand, it's unlikely you'll get it to be exactly 2. So let's go back and put these values on here. So I should get that m equals 2 and y equals 1.4, c equals 1.4. Which you should get near enough from your graph. If we now go back to this function here, which is where we were, look, I now know the value of c is log r. So I know the log of r is 1.4, and I know that n is 2. So back to here again, c equals 1.4, which equals the log of r, and m equals 2, which equals n in this power function. Remember from industrial equations, if I was told that the log of r is 1.4, what do I do to get r? Can you remember? Inverse logarithm, this is a power of 10. So 10 to the power 1.4 will give me r. So I work out what 10 to the power 1.4 is, which is somebody. And if you look at for the 10 to the power button, it's above the log button. No coincidence, because it's the inverse function to the logarithm function. We get 25.1.2. All right, okay, 25.1 to 3 significant figures. Yeah. To 3 significant figures. And we know that n equals 2, so now we can say that our power equation, therefore, we have that power equals ri to the n, so for this particular set of results, for this experiment, power equals 25.1 times the current squared. And some of you may know from your electrical work that the relationship between power and current is I squared. P equals I squared R. We compare that with P equals I squared R, which is the power equation. What we've done is confirmed it. We've confirmed that the power is 2, because we've found that to be 2. And more than that, we've calculated the resistance of this circuit. So actually, the resistor in this particular circuit is 25.1 ohms. Look back at these results. This could be some component in a circuit. Just by calculating the current and the power, I can actually now confirm that this is an ohmic resistor in this circuit, and therefore the power equals Ri squared, and I can say what the resistance is for this circuit. Just from a set of results and plotting the log function, I can confirm that it's a power relationship like this, and more than that, I can find the values of R and N. A very powerful technique, especially if it's combined with this autograph software that allows you to just put the values in very quickly and then find the equation of the line that fits it, just by changing the values of M and C. Okay. Why am I not able to do this? Go back to here. What's going on? Come here. There we go. Save